All right, so get ready, because today we're diving into something pretty wild, and that is the Planck length.
Yeah, the Planck length.
And it's funny because when I first heard about the Planck length, I was like, okay, another teeny tiny measurement, big deal, right?
Yeah.
But it's actually so much more than that. It's like this threshold where like everything we think we know about the universe just kind of goes out the window.
It does, yeah.
So today we're going deep, folks. We are diving deep into the Planck length, what we know, what we don't know.
Exactly.
And get ready for some serious mind-bending stuff. Because where we're going, the laws of physics...
They get a little fuzzy.
Yeah, they get a little fuzzy. That's a good way to put it.
Yeah.
So, okay, to even start to understand this, let's talk about what we're dealing with here, right? We're talking about 1.616 by 1035 meters.
That's right.
I mean, can you even picture that?
Well, not really. I mean, even for physicists, it's hard to wrap your head around a number that small.
Yeah.
But think about it this way. Okay. Imagine you could shrink an atom down to the size of the entire observable universe, right?
Okay, so an atom the size of everything we can see in the universe.
Exactly, like the whole shebang.
Wow.
At that scale, at that mind-boggling scale, the Planck length would be about the size of a tree.
Okay, so we're not just talking tiny here. We're talking like a whole different...
It's not just small. It's
Yeah.
where our normal ways of measuring things,
Yeah.
our everyday concepts of size and distance,
Yeah.
they just kind of stop working.
It's like the universe is telling us, nope, not going to give you a straight answer here.
That's a good way to put it, yeah.
Okay, so help me understand this. Why? Why does it break down like that?
All right, so to get that, we kind of have to dive into the realm of quantum mechanics.
Okay.
So at the Planck length, you have these things called quantum fluctuations.
Quantum fluctuations, okay.
Yeah, and these things, imagine like the fabric of space-time, right? Most people think of it like a smooth sheet.
Yeah, like a flat surface.
Right, but at this scale, it's more like a bubbling foam, constantly shifting and changing.
Oh, wow. Okay.
Yeah, and all this fuzziness, this inherent uncertainty, it means distances and time intervals are always in flux.
So you're saying even time itself is getting all wobbly at this level?
It's not even wobbly. It's like, you can't even pin it down.
That's wild.
It really is.
Okay, so what does this tell us about, like, the limits of what we know? I mean, if everything's so uncertain at this level.
Well, it really highlights the limitations of our current theories, Like, we've got general relativity, which is amazing for explaining gravity on large scales, planets, stars, galaxies.
Yeah, the big stuff.
Right, and then we've got quantum mechanics, which is awesome for explaining the really tiny stuff, like atoms and subatomic particles.
So the very big and the very small.
Exactly, but when you try to bring those two together at the Planck scale, they just don't play nice.
It's like they're speaking different languages.
Yeah, and a great example of this is the Heisenberg uncertainty principle.
Oh, yeah. The more you know about one thing, the less you know about the other.
Exactly. So the more precisely we know a particle's position, the less we can know about its momentum, how fast it's moving, in what direction, and vice versa.
Okay.
And at the Planck scale, this uncertainty just explodes.
Like it's off the charts.
Yeah, making it virtually impossible to do precise measurements.
So even the most basic things, like how far apart two things are or how much time has passed.
All up for grabs at the Planck scale.
It's almost like the universe is saying, yeah, you can try to measure me, but good luck with that.
Exactly.
All right, so this is all super fascinating, but is it just theoretical? I mean, does this uncertainty, this fuzziness, does it actually have real-world consequences?
Oh, yeah, definitely. It has huge implications for our understanding of some of the most extreme objects in the universe.
Like what?
Well, black holes, for one.
Black holes. Okay, wait, so how does this microscopic scale, the Planck length, how does that connect to these massive objects?
So black holes, they're born when giant stars collapse, right? All that matter gets crushed into an incredibly dense point, a singularity.
Yeah, infinite density, right, where gravity just goes nuts.
Exactly. But here's the thing. At the Planck scale, where these quantum fluctuations are dominant, the predictions of general relativity, our theory of gravity, they just break down.
Oh, so it's like our equations just hit a wall.
Basically, yeah. Which suggests that to truly understand what's going on at the heart of a black hole, we need a new theory, a theory of quantum gravity. Something that can marry the world of the very large and the very small.
Okay, so this is where things start to get really interesting. We're talking about potentially bridging the largest structures in the universe with the tiniest building blocks.
Exactly.
So what are some of the ideas that physicists are exploring to try and crack this quantum gravity code?
Well, one of the leading contenders is string theory. And this is where things get really mind-bending.
Oh, boy. Okay, hit me with it.
All right, so String theory proposes that the fundamental building blocks of the universe, they're not point-like particles like we usually imagine, but tiny vibrating strings, one-dimensional strings.
Okay, so instead of little billiard balls, we've got these tiny little strings, like little pieces of thread or something.
Yeah, and these strings, they vibrate at different frequencies. And those vibrations, they determine the properties of the particles we observe.
Okay, so that's pretty wild, but how does that change our understanding of the universe? I mean, why strings?
Well, for one thing, string theory requires extra spatial dimensions, more than the three we experience every day.
Wait, extra dimensions, like beyond up, down, left, right, forward, back?
Exactly. Imagine a garden hose,
Yeah.
okay? From far away, it looks like a one-dimensional line,
Oh,
right?
that's a long, thin thing.
Right. But if you zoom in close, you see it has another dimension. It's circumference, how round it is.
Ah, yeah.
So string theory says that space itself might have these tiny curled up dimensions that we can't perceive directly because they're so small.
Okay, so these extra dimensions, they're like hidden folds in the fabric of space.
Exactly.
But how can we be sure they're even there? Like, what kind of evidence could we even look for?
That's the challenge, right? It's like trying to study the fine details of a painting from miles away.
Yeah, you're not going to see much.
Right. But even though we can't directly observe these extra dimensions, string theory predicts certain effects that could be detectable in our three-dimensional world.
So even though these strings and extra dimensions are happening at the Planck scale, their effects might ripple outwards to scales we can observe.
Precisely, and that's what makes the quest to understand the Planck length so exciting.
Yeah.
It's not just about unraveling the mysteries of the ultra-small, it's about potentially revolutionizing our understanding of the entire universe, like everything.
So we're talking about like a fundamental shift in how we view reality.
Absolutely.
I'm trying to wrap my head around this. We've got these tiny strings vibrating in multiple dimensions, and it all stems from this bizarre world of the Planck length.
It's pretty wild, right?
Yeah, it is. It really is. So is there anything else? I mean, is string theory the only game in town when it comes to quantum gravity?
Well, there's another intriguing approach called loop quantum gravity, and it takes a slightly different angle.
Oh, okay, so tell me more about that.
So instead of extra dimensions, loop quantum gravity proposes that space itself is quantized, like broken down into tiny, indivisible chunks.
Wait, so you're saying space is made of loops?
It's kind of like that, yeah. Think of it like pixels on a computer screen.
Okay, yeah.
From a distance, the image looks smooth, but zoom in close enough and you see the individual pixels.
You see those little square.
Exactly. So loop quantum gravity suggests that something similar might be happening with space itself, but at a scale far, far smaller than anything we can currently observe.
Okay, so we've got string theory with its extra dimensions and loop quantum gravity with its kind of pixelated space-time.
Right.
Both of them trying to grapple with the mysteries of the Planck length. It's like we're standing on the edge of this vast, uncharted territory.
That's a great analogy. And both of these theories, while different in their approaches, they both kind of hint at this possibility of entirely new physics operating beyond the Planck length.
Like a whole new set of rules.
Yeah, a realm where our current understanding of reality might be completely overturned.
Wow. Okay, so if we ever figure out what's going on down there, what kind of revolutionary ideas could emerge?
Well, for starters, imagine a world where gravity is unified with the other fundamental forces of nature.
Okay.
A world where we finally understand what's happening inside black hole singularities, where the true nature of space and time at their most extreme is revealed. A world where, well, we can only speculate at this point.
Okay, hold on. Before we get too carried away, let's come back to those black holes for a moment. You mentioned earlier that the Planck length might hold clues to understanding them. Can you expand on that a bit?
Yeah, so remember those singularities we talked about, those points of infinite density where general relativity breaks down?
Yeah, the places where physics goes haywire.
Exactly. Well, quantum gravity might offer a way to resolve those singularities, replace them with something a little more, well-behaved.
Something that doesn't make the laws of physics cry.
Yeah, exactly. Instead of a point of infinite density, we might have something more like a highly compressed region of space-time, perhaps governed by quantum effects that we don't yet fully understand.
Okay, so quantum gravity could help us understand what's really happening inside a black hole, where gravity and quantum effects are both at their strongest.
Precisely.
That makes a lot of sense. But it's not just black holes, right? You mentioned that the Planck length might also hold clues to the very beginning of the universe, the Big Bang.
Exactly. And this is where things get really wild.
Oh, okay, I'm ready. How does that work?
Well, our current understanding of the Big Bang suggests that the universe began as a singularity, right? A point of infinite density and temperature.
Right, like the ultimate black hole.
Yeah. But just like with black holes, this singularity presents a problem for our theories.
Because it's another place where general relativity breaks down.
You got it. But if quantum gravity takes over at the Planck scale, then the very beginning of the universe might look very different from what we currently imagine.
So instead of the universe exploding from a single point, what might we have? Like a universe bubbling up from quantum foam or something?
That's one possibility, yeah. Some physicists propose that the universe didn't begin with a singularity at all, but with a quantum state governed by laws we're only beginning to grasp.
So it's like saying the Big Bang wasn't a beginning, but a transition from one state of the universe to another, a cosmic metamorphosis, if you will.
I like that. It really captures the idea that the Planck scale might not represent an absolute beginning or end, but a threshold where our current understanding of reality undergoes a radical shift.
Okay, so if space and time are fundamentally uncertain at the Planck scale, does that mean there's a smallest possible unit of space? Like a cosmic pixel, as you mentioned earlier.
That's the idea, and if there's a smallest possible unit of space, there might also be a smallest unit of time, something called Planck time, which is about 1043 seconds.
Whoa, that's incredibly fast.
So you're saying that time might not flow smoothly, but rather in these tiny, discrete jumps.
That's one of the intriguing implications of quantum gravity. It challenges our very notion of what time is.
Yeah, I can see how that would be a real headache for physicists.
It is.
But if time is quantized, wouldn't that affect everything we know about cause and effect? Like, does the future still depend on the past in the same way?
It certainly raises some profound questions. If time isn't continuous, but rather a series of discrete moments, then what does that mean for our understanding of causality? Does the arrow of time, that notion that time flows from past to future, does it still hold true at the Planck scale?
Those are some seriously deep questions. It seems like the Planck length isn't just a tiny measurement, but a gateway to a whole new way of thinking about the universe.
Exactly. It forces us to rethink some of our most basic assumptions about reality.
It's like realizing the ground beneath our feet might not be as solid as we thought it was. That's a great way to put it. It makes you wonder if we're only seeing a tiny sliver of a much grander, more complex reality.
This is all incredible, but with all this talk of string theory, extra dimensions, and quantum foam, are we just speculating here? Is there any way to actually test these ideas?
That's the million-dollar question. Directly observing phenomena at the Planck scale is far beyond our current technological capabilities,
Mhm.
but there might be indirect ways to test these theories.
So how could we do that? I mean, we can't exactly build a microscope powerful enough to see these tiny strings or loops, right?
No, not yet, at least. But these theories make predictions about the behavior of the universe that could be testable at larger scales. For example, some versions of string theory predict subtle variations in the cosmic microwave background radiation, the afterglow of the Big Bang.
So we might find evidence of these tiny strings written across the vast canvas of the cosmos.
Exactly. And loop quantum gravity makes predictions about the behavior of black holes that could potentially be observed with future generations of telescopes.
It's amazing to think that these incredibly small-scale phenomena could have observable effects on the largest structures in the universe.
It's a reminder that the universe is interconnected in ways we're only beginning to understand. What happens at the Planck scale doesn't stay at the Planck scale. It could be woven into the very fabric of reality itself.
Okay, before we go any further down this rabbit hole, I want to touch on something you mentioned earlier, the philosophical implications of all this. If space and time are fundamentally uncertain at the Planck scale, what does that mean for our understanding of reality? Does the very concept of size break down?
That's a fascinating question, and one that takes us beyond the realm of physics and into the domain of philosophy. If our basic notions of space and time are up for grabs, what does that say about our perception of reality? What does it mean for our understanding of cause and effect?
It makes you wonder if we're only seeing a limited version of reality, constrained by our own perception and the limitations of our current theories.
Right, it's like we're trying to understand a vast, multi-dimensional symphony, while only being able to hear a few notes.
I love that analogy. It captures the idea that there might be a much richer and more complex reality out there, one that we're only beginning to glimpse through the lens of modern physics. This is all so thought-provoking. We've covered so much ground today, from the mind-bogglingly small to the cosmically vast. It seems like every time we answer one question about the Planck length, 10 more pop up.
It's true. The more we learn, the more we realize how much we don't know.
Before we get completely lost in the quantum foam, is there anything else you think our listeners should keep in mind as they ponder these mysteries?
I think the most important takeaway is that the Planck length is not just a number.
Right.
It's a symbol of the limits of our current knowledge and a reminder that the universe is full of surprises. It's a call to keep exploring, keep questioning, and keep pushing the boundaries of what we think we know.
Beautifully put. And on that note, I think it's time to take a moment to appreciate just how much we don't know. It's humbling, isn't it, to think that even our most successful theories like hit a wall at the Planck scale.
It is humbling.
Yeah.
But it's also incredibly exciting, because it means there's still so much out there left to discover.
Absolutely. So for our listeners who might be feeling a little overwhelmed right now by all this, like, where do we go from here? What are some resources that they can explore to continue this journey into the Planck length?
Well, there are some fantastic books out there that delve into these topics in a lot more detail. Brian Greene's The Elegant Universe. That's a great starting point for understanding string theory.
Oh, okay. Yeah, The Elegant Universe.
Yeah, and then for loop quantum gravity, you can check out Carlo Rovelli's book, Reality is Not What It Seems.
Okay, cool. And of course, there are tons of articles, lectures, videos available online. Just a quick search for Planck length, quantum gravity, string theory.
Yeah, you'll find a treasure trove of information out there.
You'll fall down a rabbit hole for sure.
Exactly.
But, besides all that, I think something we shouldn't forget is the power of our own imaginations, right?
Oh, absolutely.
Even though we can't directly observe what's happening at the Planck scale,
Right.
we can still use our minds to try and picture these concepts, to explore the what-ifs.
Yeah.
And just ponder, like, the deeper meaning of it all,
I think that's so important to just let your curiosity run wild. Sometimes the most profound discoveries, they begin with a simple question, a sense of wonder.
Yeah, absolutely. So to our listeners, we encourage you, keep asking questions, keep exploring, keep wondering. The universe is full of mysteries just waiting to be uncovered.
And who knows, maybe one of you listening right now will be the one to make the next breakthrough, to shed new light on the secrets that are hidden beyond the Planck length.
I love that thought. And on that note, I think it's time for us to wrap up this deep dive. But before we go, I want to leave you with one final thought to ponder. What if, and just hear me out on this, what if the very act of trying to understand the Planck length, to peer beyond that veil of the unknown, changes the universe we're trying to observe?
Whoa, okay, that's a deep one. It's like, are we influencing reality just by trying to understand it?
Right. It's like if our current theories break down at that scale, maybe it's because the act of observing, of measuring, it introduces a fundamental uncertainty that we can't separate from the reality we're trying to understand.
Yeah, it's like our tools for understanding the universe become part of the universe itself at that level.
Exactly. It raises the possibility that the universe at the Planck scale isn't a fixed objective reality, but like a dynamic interplay between the observer and the observed.
That's a really trippy thought. Like, we're not just passive observers of the universe, but active participants in how it unfolds.
Yeah, maybe we're more like co-creators.
Co-creators, yeah. And that leads to some really mind-bending philosophical questions.
Yeah, sure.
Like, what does it even mean for the concept of truth or objectivity if reality is shaped, even in some small way, by the act of observation?
It's almost like the universe is a giant choose-your-own-adventure book, and our observations are the choices that determine the plot.
I love that analogy. It captures the idea that the universe might not be this fixed, predetermined entity, but a realm of possibilities that are constantly being explored and realized through the act of observation.
Okay, I think we've officially blown everyone's minds for today. From the mind-bogglingly small to the philosophically profound, the Planck length has certainly taken us on a journey.
It has, and it's a journey that's far from over.
That's right, there's always more to explore. Thank you for joining us on this deep dive into the Planck length. Until next time, keep looking up and keep those questions coming. It really is kind of humbling, isn't it? You think even like our most successful theories, they hit a wall when we get to the Planck scale.
It is humbling. But it's also, I think, incredibly exciting.
Yeah.
Because it means there's still so much more out there to discover. It's not like we've reached the end of physics.
Absolutely. So for our listeners who, might be feeling a little, a little overwhelmed by all this, where should they go from here? Like, what are some resources that they could check out to kind of continue this journey?
Well, there are some great books out there, that go into a lot of these topics in way more detail.
Yeah.
So for string theory, Brian Greene's The Elegant Universe is a really good place to start.
The Elegant Universe. Okay.
Yeah. And then for loop quantum gravity, Carlo Rovelli's book, Reality is Not What It Seems. That's a fascinating read.
Okay, cool. Cool. And of course, there's tons of articles, lectures, videos online, like a quick search for Planck length, quantum gravity, string theory.
Oh, yeah, you'll fall down a rabbit hole for sure.
Yeah, you really will. It's amazing. But besides all that, I think, you know, something that we often forget is just the power of our own imaginations.
Absolutely.
Even though we can't, directly observe what's happening at the Planck scale,
Right.
we can still use our minds, to try and picture these concepts and to explore the what ifs
Yeah, yeah.
and just ponder the deeper meaning of it all.
I think that's so important to just let your curiosity run wild. Sometimes the most profound discoveries, they begin with, like, a simple question, a sense of wonder.
Totally. So to our listeners, we encourage you, keep asking questions, keep exploring, keep wondering. The universe is full of mysteries just waiting to be uncovered.
And who knows? Maybe one of you listening right now will be the one to make that next breakthrough, to shed some new light on the secrets that are hidden beyond the Planck length.
I love that thought. And on that note, I think it's time for us to wrap up this deep dive. But before we go, I want to leave you with one final thought to ponder. What if, and just hearing out on this, what if the very act of trying to understand the Planck length, to peer beyond that veil of the unknown, changes the universe we're trying to observe?
Whoa, that's a deep one.
Yeah.
Are we influencing reality just by trying to understand it?
Right. It's like if our current theories break down at that scale, maybe it's because the act of observing, of measuring, introduces like a fundamental uncertainty that we can't separate from the reality that we're trying to understand.
Yeah, it's like our tools for understanding the universe become part of the universe at that level.
Exactly. It raises the possibility that the universe at the Planck scale isn't a fixed objective reality. It's like a dynamic interplay between the observer and the observed.
That's a really trippy thought. Like,
Yeah.
we're not just passive observers of the universe. We're like active participants in how it unfolds.
Yeah, maybe we're more like co-creators.
Co-creators.
Yeah.
Yeah. And that leads to some really mind-bending philosophical questions,
Oh, for sure. Yeah.
Like, what does it even mean for the concept of truth or objectivity? If reality is shaped, even in some small way, by the act of observation.
It's almost like the universe is this giant choose-your-own-adventure book, and our observations are the choices that determine the plot.
I love that analogy. It captures the idea that the universe might not be this fixed, predetermined entity. It's a realm of possibilities that are constantly being explored and realized through the act of observation.
Wow. Okay. I think we've officially blown everyone's minds for today. From the mind-bogglingly small to the philosophically profound, the Planck length has definitely taken us on a journey.
It has, and it's a journey that's far from over.
That's right. There's always more to explore. Thank you for joining us on this deep dive into the Planck length. Until next time, keep looking up and keep those questions coming.